For my final year project, I created a prototype of an application for vocal pitch and timbre control training. I wanted my project to combine my passion for singing and music with my interest in the area of digital signal processing, which has been an integral part of my degree. I also wanted to explore the field of machine learning so that I could learn something during my project that was not included in my degree. Initially, I had the idea of creating a vocal pitch tuner, as I felt it could support users like myself in their vocal training when and if they are unable to attend or afford face to face vocal coaching. However, once you reach the basic level of pitch control, vocal coaching focuses on gaining better control of the different timbral characteristics of your voice, like vibrato, brightness, and breathiness. Therefore, the idea got developed into creating a vocal tuner that displays both pitch and timbre, as timbre has a huge impact on vocal quality and whether the sound is appropriate for a genre or style. I looked into a few existing solutions and found hardware solutions called vocal trainers, which display pitch information only. Software solutions exist that display timbre information. Sing and See is a desktop application where the timbre information is displayed as a spectrograph. This isn't easy to interpret in real time when using the application. Cortosia displays pitch and timbre in a way that is better for real time use, but it isn't developed for vocals. Therefore, I decided to develop a desktop application which displays both pitch and timbre characteristics of the voice in real time. The system is designed to analyze pitch information using the fast Fourier transform and detects pitch based on the highest FFT peak. The system analyzes the FFT peak bandwidth to determine whether a note is stable or contains vibrato. It uses a k-nearest neighbor algorithm to label the timbre color and volume. Here you can see the graphic user interface design of the implemented prototype. The timbre is displayed by connecting the appropriate timbre characteristics with yellow lines. The timbre color and volume are labeled using a binary classification system, so the timbre color is labeled either as bright or dark, and the timbre volume is labeled either as hollow or full. The vibrato of the input is displayed as maximum vibrato, maximum stability, or in a state between the two based on the FFT peak bandwidth. Pitch is displayed on a grid system. Now we will have a closer look at the implementation of the prototype. All required libraries are imported. All these libraries must be installed on the device for the program to run on it. The function load data is used to load the data from a CSV file. The program's general settings and variables are defined on lines 42 to 65, which include things such as the default values for display text and pens. The paths for the input audio recording and CSV files for the timbre color and timbre volume datasets are also defined here. When running the program on a different computer, these paths must be updated to reflect the paths used to access the files within the specific computer. The datasets are loaded from these paths using the load data function. The class coordinates is used to store the coordinate values required to draw timbre display lines within the hexagon. The class timbre is used to store the input file timbre labels. The class peak is used to store the low and high frequency values of the second FFT peak, which is used by the program to determine the peak bandwidth. The vocal tuner class defines the main window of the application, which is displayed once the program is running. To set up the window, the program uses the function paintEvent to draw everything seen on the display. It uses the function drawStatic to draw the elements of the system which do not change during input. This draws the pitch grid and timbre hexagon, which is defined by the createHex function. DrawShapes is used to draw everything that changes during the use of the application. The application also displays static text using functions appText, pitchStatic, and timbreText. The vocal tuner class defines the text of the input note name and the note names of the limits of the pitch grids as elements of itself so that these can be changed as the program runs. A timer called QTimer is defined within the vocal tuner class to trigger the system to update the display. Each time that the QTimer times out, it calls the update values function used to reset display values and refresh the display. The QTimer timeout interval is set to 2 milliseconds. When update values is called, the pitch and vibrato of the input are calculated for display by calling the function noteSet. NoteSet calls the function findFreq, short for find frequency. The find frequency function opens an audio stream from the device, checks whether the output crosses the threshold amplitude, smooths the data window using a Hanning window, and calculates the FFT frequency spectrum. It calculates and returns the input frequency based on which frequency bin has the highest amplitude. The input FFT information is also used by the function findPeakStartEnd to set the start and end points of the second FFT peak by setting these values in the peak class. These are used later in the program to calculate the FFT peak bandwidth for vibrato detection. NoteSet takes the frequency outputted by findFrequency and uses it to attain the nearest note number, frequency, and name. It also calculates the cent difference between the actual input frequency and the closest note frequency. Update values uses this information to determine the appropriate labels for the upper and lower limits of the pitch grid and the color and size of the pitch bar to indicate how off the input pitch is from the target note. Update values also calls the audio in function to record a short snippet of the input stream into a file of the same length as the files in the loaded datasets. The file name is sent to the assign timbre function and is processed by the getTimbreKNN function, which calculates the input file's MFCCs and compares these with the dataset's MFCCs. 2 KNNs are used in total, one to determine the K closest neighbors based on timbre color, and another to determine the K closest neighbors based on timbre volume. The encoded predicted labels of the input are returned to assign timbre, which decodes these labels to set the input timbre volume and color labels in the timbre class accordingly. The timbre coordinates function is used to determine the coordinates used to display the timbre based on the input. First, it calculates the bandwidth of the second FFT peak based on the peak start and end points calculated earlier in the program. Depending on that value, the coordinates are set to display maximum vibrato, maximum stability, or a point between these two states. The timbre color and volume are used to set the coordinates to display the input as dark or bright and hollow or full as determined by the KNN output. After all these values have been recalculated, the display is updated. Values are recalculated once the Q timer reaches its timeout value again. The application is set up and shown until the user exits the application using these 4 lines of code. Here is a demo video of the final implementation. The application can be run via the terminal by calling the correct file path. It starts with a blank display in blue to indicate that input has not been detected. Once input is detected, the system displays pitch and timbre. When a note is sung without aiming to create a specific tone, the timbre labels fluctuate. However, when trying to generate specific timbre characteristics, the display tends to be more stable. In this example, the timbre is labeled as expected, but pitch detection is slightly off. When singing a full and bright tone at an octave higher, the pitch detection and timbre labels are accurate. These variations in pitch detection could be due to the natural overtones of the test voice. The natural vibrato is not fully controlled, which is why the system displays the input in a state between stable and vibrato. The application usually reacts appropriately when adding vibrato to the voice. The labeling of timbre color is not dependent of pitch. Notes at higher octaves are sometimes labeled as dark, while those at lower octaves can be labeled as bright, as seen here. Typically, the test voice is labeled as bright. This is because the voice is compared to different voices in a dataset rather than itself. If the system was configured to the user's voice, it could better display how their natural tone changes. The application can be closed by clicking the red button at the upper left corner of the window. The system detects pitch accurately 85% of the time. Pitch detection could be improved by implementing it using a different method than FFT peak detection. Vibrato is detected using FFT peak bandwidth analysis. Its success rate varies with different sounds and is less successful for certain vowel sounds, such as I. The timbre labels sometimes fluctuate a lot when using the application. This could be improved by scaling all timbre labels rather than using a binary classification system. Occasionally, the system takes a while to react correctly to the input. This could be due to the way the program is structured and could be improved by using multi-threading to allow for parallel processing within the application. Overall, the project was successful in implementing a prototype of a vocal pitch and timbre control training application, which can be developed further before release. Pitch detection is accurate 85% of the time. Vibrato detection was successful about 63% of the time when labeling vibrato and stability in a binary system. Now that the system is scaled, the accuracy is over 60%. Timbre color labels are accurate 65% of the time for the integrated design, but when testing the K&N on its own, it was accurate 89% of the time. And the timbre volume was similarly accurate 77% of the time when used in the integrated design experiment, and 94% of the time when experimenting on the K&N algorithm on its own. So the total implemented accurate performance of the system is 71 to 90%.